Starting, all attendees are in listen-only mode.
Good afternoon, ladies and gentlemen. Welcome to TechGig webinar series, our endeavor to empower techies. We believe that sharing of knowledge is the key to enhance our skills and grow us as professionals. With this principle in mind, we have initiated a series of webinars conducted by industry experts to give you all a crisp insight of various domains. The topic of today's session is REST APIs in cloud computing. And our guest speaker today is Basavaraj Kodkali. He is the architect with Manipal Global Education Services. Basavaraj has more than 12 years of experience in designing and building distributed and web-scale applications for healthcare, enterprise, finance, and training and education domains. So without further delay, I introduce you all to our guest speaker. Over to you, Basavaraj.
Thanks, Radhana. Hello everyone, and a very warm welcome to today's discussion topic. I hope you all can hear me clearly. In case of any issue, you could contact Radhana for any help required. Today's topic is REST APIs in cloud computing. Today's topic is mostly motivated by the issue that many people talk about REST APIs or the cloud computing in isolation. However, both together when applied is when the cloud computing is really truly meaningful and really helps you in taking the cloud to the next level and making most out of your infrastructure. So we will go about discussing this topic today, and let me introduce you to today's agenda or the scope that we will be discussing. So we will start with introduction to REST architecture. We'll also understand how are these REST architecture constraints are derived and defined, how they benefit in web concepts. We'll also outline the cloud computing concepts or the characteristics, challenges, and some of the good cloud challenges that we need to address using the REST. We'll also, in the end, see how the cloud computing challenges are overcome using the REST architecture principles and the concepts. With that, we'll move to discussions towards the end of the session. Let me now introduce you about the REST as a representational state transfer, as it stands for REST. REST is actually a network-based architectural style for distributed hypermedia systems, such as the World Wide Web. REST can not only be applied to World Wide Web, but any of your intranet web application which makes use of hypermedia as a computing platform can also be applied. REST was originally introduced by Roy Thomas Fielding in 2000. Roy Thomas Fielding introduced REST as a more of constraints-driven RESTful architecture for distributed hypermedia systems, which means that REST will not impose any additional requirements on the World Wide Web in order to achieve its principles and the benefits it states to derive. It also makes hypermedia as the engine of application state change, which means you would be using hypermedia as your state machine. Without implementing any workflow engine, you can make use of the hypermedia itself as your workflow engine. Overall, REST mainly emphasizes on scalability of component interactions and generality of interfaces. These two concepts are like overarching concepts which define broader RESTful constraints as well as provide a broader benefit to the web systems. Before continuing with the rest of the topic, we would like to start with a poll so that we know our audience well. Aradhana, can you please provide the polling?
Yes, Basavaraj. Are you able to see the poll window?
No, I'm unable to see the poll window.
All right, let me just tell our audience about the poll a little. It's your familiarity with REST and cloud. And you can select the options from new to the topic, aware but do not understand the topic, understand cloud but not REST, or understand REST but not cloud. Can we close the poll now, Basavaraj?
Yes, we can.
And the poll is over, so do let me know whenever you would like to know the results.
Okay. Right.
And the results of the
Can we
poll
know the
is,
results?
yes, Basavaraj. So the result for the poll is 34% of our audience has said they are new to the topic. 32% have said that they are aware but do not understand the topic. 15% have notified that they understand cloud but not REST. And 20% of the audience have said they understand REST but not cloud.
All right. Thank you very much. All right. So we will move on to the defining of each architectural constraints of REST, and we'll spend more time in understanding those since majority of the people are new to this topic. Okay. So REST mainly lists 5 architectural constraints for the network-based or the distributed network systems. One is client-server. It is meant to separation of concerns. We'll see more in detail about that. Second, stateless communication. All your client-server communication should be stateless so that the scalability can be infinitely increased. We also discuss about cache as the key architectural constraints by REST. Uniform interfaces, which is the key distinguishing point of REST architecture style. Last, layered is one of the key component-based architectural style of REST. In the end, code-on-demand, which is not a mandatory constraint but an optional constraint imposed by REST architecture style. We'll discuss each of these in more detail in a little while. So once again, repeating the constraints: client-server, stateless communication, cached, uniform interface, layered, and code-on-demand. Let's have a look at each of these constraints in detail now. What you are seeing is here a client and a server. The very first and the very basic constraints applied by REST. REST defines that any two nodes in the network or the distributed network has to be connected and operated as client and being a server. The reason being, we can separate the concerns of input-output of data with that of processing of the data. Over here, what you see is a single client and a server. In a normal operational mode, client takes the inputs and sends the data to the server. Server processes the data and returns back the data or the response to the client. Client once again uses the response and offers it to the user using the client. This is how a basic client-server communication is established first in the place. So why are we doing the separation of content? What is the benefit of doing so? It is simply because anywhere when we separate the contents of data and its processing, we can add more number of clients to the server. Because we have now separated the input-output and with that of processing, more number of clients can now connect to the same server, which is the key and the basic or the fundamental constraint imposed by REST architecture, where your client and server have to operate like client and server, one being the input-output handling, the other being processing this data and returning back the response. We will in detail list down the benefit of this when we would also take up the cloud. Let's move on to the next constraint, stateless. Stateless constraint is second most important principles or constraint in REST architecture. Stateless simply doesn't mean that application should not have any state. Developing an application without a state engine or a state would be really boring and of no much use. REST principle states that the communication between client and server or the communication itself should not have any state information stored on the server. The reason being, storing any state on the server would complicate the things in terms of reliability. Hence, server transfers the state information to client. Because the state is not transferred to the client, a client can talk to more than one server to do the same job or to execute the same workflow. And a server can talk to multiple clients to execute the same job. Imagine a workflow where a workflow starts on a mobile application but ends on a PC or even a tablet. Such kind of web transactions or workflow is possible only when your client and server communication is stateless. So how is it exactly derived in terms of programming or in terms of more concrete understanding? Stateless simply means that when a client makes a request to the server, client should provide all the data or the state information to the server which is required or needed by the server to process the request and return back the data. That is what the stateless actually means in terms of REST architectural constraint. You will see that how stateless server or the stateless communication makes humongous impact on scalability of distributed hypermedia systems. With that, we'll move on to the next architecture constraint. Cache, as simply known, I think many people understand cache as data stored locally. However, in terms of architectural principles, cache is a very important thing and plays a very significant role in terms of quality attributes of a network architecture. As you can see, there are more than one client communicating with the server. However, when number of clients increases, your servers will have to be increased as well. So often, 99% of the time, the data would mostly look the same or static, or it is almost not changing within the shorter period of time. Still, clients make a trip to the server and eat up the network bandwidth, hence impacting the efficiency of the network systems. In order to address this, REST talks about caching of data in more than one places. As you can see on your screens, we introduced cache on multiple places. A cache can be on your PCs or on your local network or even on your corporate firewall or even on network gateways or even on your internet provider gateways. Even many servers employ reverse caching, where many of the frequently hitting requests will simply get back the data with the HTTP response code of 304, which simply means the request did not got processed but simply returned back using the already cached data, which is as good as processed data. This is made possible by explicitly labeling the responses as cacheable or non-cacheable by the server, which is implementing the RESTful architecture. With this labeling, many of your PCs, browsers, systems, or the proxy servers know whether they should cache the data and return back the data to their clients or not. Wherever the data is marked as cacheable is cached with an expiry time limit, and the same data is returned back to the client whenever somebody requests for it. This is extremely valuable when you look at the mobile or the tablet or even a TV-based communication. It vastly improves your network bandwidth and reduces the latency. Let's move on to the next architecture constraint. Next architecture constraint is uniform interface, which is the key differentiator for defining REST. Uniform interfaces simply means generality of interfaces. That is, the communication between client and server should be in a uniform interface so that standard mechanisms can be applied. On your screens, you can see that the client and servers each connected are having a standard interface. They are communicating over a standard interface. Not only the client and server, because it is uniformly interfaced as well as it is cacheable, any of the intermediaries like your PC browser cache or even the proxy servers or gateway proxies too can cache the data using this uniform interface and can still communicate the standard mechanism. You will see that uniform interfaces translate into URIs or the URLs, which simply means that it is a unique identification for the resource you are accessing over the web, which is served using the server. We'll go to the next architectural constraints. As you can see now, we introduced client and server, and then we introduced caching, and then we introduced uniform interfaces, which enables us to talk to different servers irrespective of the topology of the network servers. Topology never remains the same across multiple platforms and multiple devices and multiple technologies we use in modern world. Because of layered architecture constraints, we can achieve n number of innovations and benefits. Today, almost all complex web applications are layered. In terms of REST architecture constraint, layered simply means that a component within a layer talking to another component can only know about the layer details of the immediate component it is talking to. It need not necessarily know anything about any other layer or the component outside of its layer. This abstraction helps scale or introduce new abstraction layers without impacting the other layers. Thanks to the uniform interfaces, it makes it even more simple and manageable to introduce newer layers. As you can see on your computer, we have shown you news and content and weather as the three different layers, whereas all the clients or the PCs, mobile phones, and tablets are connecting to a news server, which in turn is layered for content separately and the weather separately. So when a client requests to the server aggregates the data or can collect the data from both content as well as the weather server and offer it as a single response to all the clients. We can easily introduce a share market server in between this layer and also offer share codes and share prices to these clients. This is how layered architecture constraint is useful because of the REST principles. All right, with this, we'll move on to the next architectural constraint, which is CodeOnDemand. CodeOnDemand REST architecture constraint is an optional constraint simply because of the security constraints that may be there in the network architecture. CodeOnDemand in REST indicates that along with the data or the metadata that is being passed by the server or the state information passed by the server to its client, server can also pass on code which can be executed by its clients. This is avoided or blocked in many of the conditions due to the security concerns. However, with the modern day JavaScript and rich web client technologies, this is no more a thing to worry, but many places this is not allowed. However, this is an optional constraint and hence care should be taken so that if anywhere or in a network this kind of code passing is blocked, it will not break your system. We'll discuss an example of this and benefit of this with respect to cloud architecture in a little while. So let us summarize once again all the REST architecture constraints that we discussed about. We discussed about the client server, which is a separation of concerns, mainly in terms of user interface and data storage, which allows components to evolve independently also makes the servers know nothing about the client and only client know about the server. The second constraint, stateless. Client-server communication should be stateless. Session state is never allowed to be on the server. Each request from client must contain all the data or the information necessary for the server to process. The third and fourth, cache and uniform interfaces equally enable the scalability, manageability, and bandwidth in the network architecture systems. The last two, layered code-on-demand, are another two key essentials for REST principles. We will now discuss more about cloud, and we'll go on about discussing how cloud is beneficial for us, and we'll apply the REST architecture to solve some of the cloud challenges. If you have any questions on the REST architecture constraints that we discussed so far, you can type in your questions. I'll come back to you later towards the end of the session. All right. Cloud is an ubiquitous computing platform, which is a buzzword in the recent times. Here you are seeing the characteristics of the cloud, which are defined by NIST, National Institute for Standards and Technology. As per these characteristics, any cloud service which is offered should follow these characteristics and fulfill them, which are on-demand self-service, which means provisioning of computing resources without having human interaction, which means any customer can add or remove more resources without any administrator's intervention. A Dropbox service, which is a cloud storage, is a wonderful example of the same. You can buy plans of different storage capability or capacity without really having to go through any salesperson or an administrator. Same way, broader network access. Broader network access is another characteristic of cloud computing, which simply means the cloud service should be accessible using standard mechanisms over heterogeneous platform. Whether the platform is a thin client, thick client, or a mobile device, or a tablet device, or a Linux, or a Mac, or a Windows, or any other platform, it shouldn't make any difference. It should serve all these platforms uniformly. Resource pooling. Resource pooling simply means any resource can be allocated in a multi-tenant model, independent of the location and network topology the client is utilizing them from. It also gives rise to the requirement of rapid elasticity. Because the resource is pooled, it should be quickly and rapidly allocatable or removable from a particular customer. Hence, we prefer it to be automated. The last but the most important of all the characteristics, cloud services should be measurable. Simply because many of the cloud services are built or priced on the basis of usage, or as you go on your usage, or as based on your elasticity constraints. Hence, all the resources usage should be monitorable, controllable, and should be able to report them. Hence, there is a transparency in the measurements done at your cloud service. These reports should also be available for both the consumer as well as the provider as well as the brokers involved in the cloud services. We'll see who are the cloud providers and brokers and consumers in a little while. So these all are the advertised characteristics of a cloud service. However, the realistic expectations are completely different. Let's have a look at them. You might have seen many of your organizations which simply migrated their application from private deployment environment to the cloud environment, mainly wanted to do that because they wanted to reduce the IT cost. Many organizations or customers believe the cloud as a simple software platforms and infrastructure services. Yes, it is true. Cloud computing offers software platforms and infrastructure as a service, just like your utility services today. Hence, many of the customers who use cloud computing as a service are leasing the infrastructure rather than owning and maintaining, getting rid of the burden of owning them and maintaining them. It also helps leveraging in high-quality infrastructure at a lower cost and with the efficiency. IT companies which manage infrastructure no more can harass their customers on the basis of the expertise they have specialized in. The expertise now available at a much lower cost and with more standards at an affordable price. Users also expect an instant infrastructure to be available for them using the cloud. Just like how automobiles are expected to go from 0 to 80 in seconds, customers expect their infrastructure to take from a 0 server to n number of servers within seconds. And today's cloud services very well offer the same. Customers also expect if the software is designed very well to take care of the cloud infrastructure, revenue can be very huge. A topic which we will discuss in the next few slides. There is also expectation to reduce the human effort and dependency, which makes up for the large amount of cost involved in maintaining application or the large web applications. We'll just discover now how these expectations are handled. Before we go on using or before we are exploring these problems and addressing them, let's have a look at the standard service model offered by all the cloud providers, all the cloud platforms. Here you are seeing a standard reference architecture for cloud-based systems, clearly indicating the cloud consumer, cloud provider, and the cloud auditor and cloud broker. Cloud consumer is the end user of the cloud services. A cloud provider is the one who is offering these cloud services to the cloud consumer. Example could be Salesforce, Amazon, Google, Rackspace, and many more. Cloud broker are the one who resells the cloud provider abilities to the cloud consumer by offering value-added services, such as RightScale, who resell the Google Cloud platform to their customers by rightly managing the cloud services on behalf of their consumers. Here you can see very well in the cloud provider there are only 3 colored components which are the service layers, which make up the service layer and is also our service models, which are infrastructure as a service, platform as a service, and software as a service. Let's take an example of infrastructure as a service. It simply refers to any of the computing infrastructure available over the cloud, such as database services or your storage or computing resources. Windows Azure, which offers such infrastructure as a service, has been largely popular. So is Amazon Web Services. You can know that in Amazon or in Windows Azure, you can take a large computing resources as your service, and you can put your application on them without any manual effort. Same way, platform as a service offers many software platforms as a service, such as cloud delivery network, as well as some of the database platforms. Next is the software as a service. Software as a service is a platform service which is offered by specialized software systems for the consumers. It can be even Facebook, it can be even Twitter. All such applications are softwares which are offered as a service. Let's now take a look at some of the characteristics of a good cloud and their challenges so that we can address them. Here we are looking at the characteristics of a good cloud. A good cloud should be scalable. It simply means it should adhere to the architecture principles of increasing resources should result in proportional increase in its performance. A good cloud should also be operationally efficient by minimizing the manual administration or the manual effort involved in managing the cloud services. It should also be designed for failure or fault tolerant, which simply means that cloud services cannot fail simply causing inconsistencies. It should be always be available, and it should be in a consistent state all the time. In case of any failure, the cloud services should have the capability to inform all the stakeholders so that the mistake can be corrected. A good cloud should also be elastic, available, and rapidly elasticity is required. A dynamic scaling with minimal manual operation effort or an automated scaling is what everyone desires, and that should be a good characteristics of a good cloud. Also, a good cloud should adhere to the economic scale of the people who pay the bills for your cloud services. They look at the cloud more as a capital expenditure being converted into operational expenditure. Hence, simply migrating your application to cloud will not help take maximum use of the cloud. Hence, a good cloud service should be able to distribute its load on all the resources it is having, and it should be able to run well with the fewer computing resources. One of the key problems addressed by REST, which we will see in a little while. All the cloud services also should be decoupled very loosely so that interoperability can be easily achieved. You may see that there are many number of mashups or Internet of Things which are available today, or a single page that you may visit on any of the websites is no more coming from a single vendor or a single service. It is always distributed with multiple vendors doing multiple things on your single web page, such as you go to a website or a Facebook app where you read an article, you like it, and you click on tweet it or like it or share it, which is again shared on the different vendors' system. It all is easily possible to do provided your cloud service is interoperable, which is again solved by the REST principles. Let's have a look at the challenges of a good cloud service. There are multiple challenges, not just one or two. However, here I have listed few of them, which seems to be more important to today's world. Cloud services are always work on heterogeneous networks, which means cloud services can be accessed via PC, via a tablet, via a mobile, or even any other connected device, such as your fridge or TV. The other challenge is to match the capacity with the load increase. A simple effect like slash dot effect, which is recently happened when WhatsApp was acquired by Facebook, the number of hits on WhatsApp was too many. Such spikes in your load should be handled using your same capacity by your cloud service. However, because of the heterogeneous quality, different components may scale in a different way. So, overall, these are the other listed challenges, such as avoiding of in-memory state, reliability, automated resource provisioning, security, measurability, cost per unit, and the spreading of the cost and risk around all the available resources in the cloud. Now let's see how our each REST constraints help addressing these problems. All right, the first REST constraint which we discussed, client-server computing. Let's see what are the problems addressed by the client-server, such as using client-server constraint, servers no more know about their client, and only clients know about server. It simply means we can add or remove n number of servers at will. Same way, client-server also allows us to scope the boundary for the connections between client and server, an important attribute of any network architecture to enable security and even to monitor. Because we also did the separation of concerns, portability of clients is achieved. That is, server can evolve and handle any kind of clients that are requesting its services. Hence, broad network challenge can be now addressed. Same way, next is the stateless communication. Because of the stateless communication between client and server, more than one server can handle the workflow request. We already saw an example of that. Same way, because now our servers do not store any state information on there, or the client is passing all the required data to the server required to process the request, we can increase the resources and we can achieve the increase in performance, which is the textbook results for scalability. Because servers do not store any state information on them, servers are impervious to reboots, network outages, or even any kind of crashes on the client side. If a workflow is abrupted either because of the network outage or a client crashing, client can simply take the earlier saved state from server and can update it or can continue with its workflow. Thus, there is an absolute fault tolerant system achieved. Because state is now shared across the clients of the server, visibility to state is available with all the clients and its intermediaries, such as the caching systems. All of this helps us increasing scalability, elasticity, and resilientness of the cloud services, which makes the cloud much more reliable than ever. Next, let us have a look at the cache, how it addresses some of the REST problems and the cloud challenges. Because we can cache now at our PCs, our browsers, or our company proxies, or the internet provider proxies, latency will be largely reduced. The direct benefit of this is on your mobile phones and tablet devices, where network is not reliable and latency is huge because of the local caching. this latency can be largely reduced. Because response can now be cached by your browser, local proxy, or anywhere within the network, entire network is a resource for cloud services. Hence, your system can be scaled out using all the network resources which are available, not just the resources that are being used on the cloud. Hence, it saves a lot of bandwidth and efficiency of your cloud services. Thus, improve the scalability of your cloud services. Next is the uniform interfaces. Uniform interfaces were newly introduced. Earlier to this, whenever a distributed web or a distributed hypermedia system was to be developed, it has to be developed using the same implementation library. You might have seen that whenever a Java program wants to communicate with a .NET or a C++ application, we used to use COMs or DLLs, which is no more required with the help of RESTful APIs. Because now resources are identified uniquely and manipulated over hypermedia, uniform interfaces offer a standard mechanism to develop the web applications. Because the resource identity is standard, it allows the network topology to be greatly innovated, hence makes the network reliable to a large extent because we now have a standard messaging syntax. Same way with the network topology and complexity in addressing network applications. All this allows measurability and evolvability of your cloud services because having uniform interface allows us to remove or refactor the server component with a better quality one without impacting any of the clients. Let us have a look at the next problems addressed by REST. Layered architectural constraints. Layered architectural constraint is already seeing the benefit of making the system stateless. Because the system is not stateless, any number of layers can be introduced or the complexity can be distributed among multiple layers, such as caching layer, queuing layer, or even the data aggregating layer. A lot of the current day technologies like MapReduce, NoSQL databases, what you see, are a direct result of this layered architecture fashion. Because REST allows you to design your system to be layered, you can introduce a distributed NoSQL cache. You can also introduce a queuing engine so that the latency can be handled separately. You can even make a REST call asynchronous using this. Hence, layered architecture makes a big impression on your network architecture by reducing the complexity and making the system available all the time. Because a layer 1 fails, you can easily introduce a layer 2 or you can fall back on a second layer. It also allows you to incrementally improve the security within the system. Because of the uniform interfaces, now we can change the layers or we can improve the layers without affecting one another. All this benefiting the cloud applications very naturally and need of the hour by all the cloud service providers. In the last, we'll see CodeOnDemand, which is an optional constraint. A very good example of this could be that when a client requests the data from the server also sends a metadata. Along with the metadata, it also sends a script which can be executed on the client side. Such as when you connect to a web channel via the REST API, REST data returned to you will also contain some JavaScript code which can convert the weather data into a different units. because often weather is seen as Fahrenheit or Celsius depending on the locality you are in, which can be easily converted using this script provided by the server itself. Thus, server has a consistency in the data which is being processed by the client server. However, because this is an optional constraint, because of the security reason, if some browsers block such passing on JavaScript or blocking certain script, your application should be able to still work with making additional requests back to the server and should not break any of your application features. Because of this constraint, we can address and manage complexity to a large extent. We can even measure the perceived speed at the client side using this technology. A lot of, or even like Google Analytics, make use of such scripts executing on the client side to track the usage and the performance of their systems. With this, we move on to the summarizing what we discussed today. So we discussed today about REST, which is a network-based architectural style for distributed hypermedia systems. It offers 6 constraints, out of which 1 is optional, starting with client-server, stateless, cached, uniform interfaces, and layers, and optional constraint being code-on-demand. We also saw how REST solves some of the major network architectural problems which are inherent to the cloud services. We saw how REST can help in making your cloud services scalable, more elasticity, more reliable, and more easily manageable, almost without any human intervention. REST also enables interoperability in the ecosystem of hypermedia system. As a result, today you see many self-building applications. Simply provide the REST API endpoints, and there are many application websites which can build the application for you, such as the Internet of Things. Hence, we conclude today's discussion that RESTful characteristics are a natural fit for designing cloud services. Hence, any developer or an engineer who is looking to build a cloud service should definitely consider REST as one of the basic and fundamental necessity for building such cloud services. Thanks, and we now open for any suggestions, feedback, or for any questions if you may have.
Thanks for the insightful presentation, Basavaraj. Let's quickly take up the questions now. I request you to read out the questions and their answers so that all our users may listen to your insights. Are you able to see the question in your question doc, Basavaraj?
Yeah, I'm trying. Okay, I do see a couple of questions.
Taking them, Basavaraj?
Okay, I'm taking up one by one. I'm seeing a question from Uvashri Suresh. What is a proxy and how it would be act in REST? A proxy could be any kind of proxy server that simply caches the data and relays back your HTTP request to the actual origin of the request or the server. How it can help in REST? As I stated, RESTful architecture constraint explicitly requires the response to be labeled as cacheable or not cacheable. When a data or a response is labeled as cacheable, proxy servers caches them and stores them in their local storage, so that when next time your browser or your client makes a request to the same request, proxy simply provides us locally stored data instead of making a big trip back to the server. This is how proxies help in case of the REST. I hope I answered that. I have the next set of questions from Brijesh Shah. Is lettered architecture best for REST development? I'm assuming what you are mentioning is the REST architecture best for layered architecture? Layered architecture principle is not only specific to REST, it is employed any service-oriented architecture recommends a layered architecture. Layered architecture simply means a component should only know or need to know only about the immediate layer it is interacting with. Hence, it provides a greater abstraction to all the other layers in the system and reduces the dependency. As much as the components are less dependent on each other, that much it is better for scaling your application. Hence, yes, layer architecture is best for REST. We could discuss on the discussion board of the TechGig to really discuss it more in detail, and I can even give you some examples. I have another question from Syed Ibrahim. How to achieve increased security in REST? REST itself is just the architectural principles. Many people ask me what is the difference between an architecture principle and the design. Simply, architecture always define the constraints. They never define example solutions. Hence, REST defines uniform interfaces so that these uniform interfaces can be monitored and security can then be applied. However, there are multiple paradigms or multiple libraries and architectural concepts which have come up. If you just want to make a REST architecture or a REST-based application more secure, you should use OAuth for identity management, and you should make all your HTTP communication SSL-based security. That is, both OAuth and HTTPS will make your REST architecture much more secure. Apart from this, on your server side, you can employ n number of tools which are available off the shelf today to monitor your REST API requests and identify any phishing or any kind of spam attacks. You should use them so that your REST can be made even more secure. However, employing HTTPS and OAuth itself will incrementally increase the security of your system.
Sorry to interrupt, Basuraj, but due to time constraint, I have to request you to take the unanswered questions offline, which I will share with you through email. So if you would like to take one last question and then sum up the session for today, you can do it now.
Sure. I have one more question from Uashri Suresh. How REST will be good when developing .NET application, and what are the settings to be done in .NET End? As I said, REST is defining uniform interfaces, and it is also transferring all the state information back to the client. And in a REST architecture, really there is no language-specific semantics involved. REST can be implemented by any programming language, where client can be in a different programming language or an implementation logic, whereas server can be entirely in a different logic. The best example for this is Salesforce, which is completely independent of all the programming languages, and it has many more clients which are running using Salesforce.com, developed in heterogeneous environments. And REST will be good, definitely, whether you use .NET or Java or anything. However, if you are seeking help on how to enable REST application or how to write a REST client using .NET, there are n number of libraries or client libraries available on the Microsoft website, which you can use so that you don't have to do all this once again. Anuradha, back to you.
And I'm really thankful to our guest speaker today for conducting this wonderful webinar. It was indeed a great session. Would you like to sum up the session for today, Basavaraj?
Sure. Once again, thanks for all you wonderful people for attending today's session. Thanks to TechGig also for providing such an opportunity. In cloud computing, definitely REST is a basic need, simply because if you look at any of the startups that are coming up in today, all the startups host their application as a cloud-based services, simply because of the enormous amount of capability offered by the REST services. You take any single startup company which is offering a cloud service, they all are enabled with the REST APIs or their services is a RESTful web service. However, RESTful web service, not all RESTful web services are truly RESTful. There is a maturity model defined by Richard, I think which you all should take a look at it. And I can offline, I can provide the references for the same. Hence, a REST principles or a RESTful web services is the first and foremost architecture every developer should know if they want to take advantage of cloud services and want to develop their own platforms and applications which can easily be scaled and integrated with all the web-related applications we have today. REST is an important knowledge and it should be applied not only for your web services, for any kind of systems that you build. So go out and read the book called REST Services Cookbook by author Subbu Allamaraju, which is a very great resource for knowing more about REST and its application to cloud computing. So, thank you once again.
And I would also like to thank all our participants for their support in making this webinar a success. The recording of the webinar will be available on techgig.com by tomorrow. Thank you all for joining us today. Thank you, Basavaraj, for all your time. I hope you have a great evening ahead.
Thank you. Bye.
Bye-bye, Basavaraj.